Okay, so the question was, what is mass? And I'll actually give you a definition that I like, that I've invented, but it's a bit of a poetic definition. It's not very practical, like a philosophical definition, or philosophical even, since I'm Eugene the philosopher. But in order to understand what is mass, let's take a look at where it's appearing first and foremost. There's only two places really where it appears. It's like mechanics and gravitation. So in Newton's laws of motion, Newton's second law is formulated as such that mass is basically the proportionality coefficient between acceleration and the force. The force is acting on the body and the acceleration it receives from these forces. So this describes what? Basically the mass as a measure of inertia of a body, right? How reluctant it is to change its state of motion with respect to, the forces acting upon it. That's the first thing where mass appears, and the second thing is the law of gravitation, okay? Where you can see it's big G times two masses divided by a distance squared, distance between them. So these are really two aspects of mass. So a mass is a measure of inertia, and a mass is a measure of gravitational attraction. And that's why sometimes, by the way, people talk about these gravitational masses in like they divide them in two, if you wish. So one property is like active gravitational mass is the kind of the ability of a body to generate its own gravitational field, and passive gravitational mass, which kind of is a property of a body to sort of react to external gravitational field, if you know what I mean. But these are basically the same, right? But I mean, in some specific formulations of certain theories, you might perhaps make such a distinction. So there you go. Mass is a proportionality between the force and acceleration, firstly. That's Newton's second law. Or it is a property of a body to react to or produce gravitational fields, okay? And we have the equivalence principle, which states that these two masses are the same. However, if you look at the laws themselves, here we have F equals ma, right? And here we have not just m's and like, some sort of spatial value, which is r in this case. Here was acceleration. But also g, right? So you might think about g, the gravitational constant, as sort of like or rather a square root of g, as a proportionality coefficient between the gravitational and the inertial mass. You might think about it in this way. But these m that we see here and here are considered to be the same. So basically, any disproportionality between these two masses, the gravitational and inertial one, is swept under the rug into this g. And what do we know about g? It's the worst known constant, in thick air quotes, constant of nature, right? It has been found that it actually might even change in time, like with this periodic 5.9 year oscillation, okay? So maybe the equivalence principle is it's a little bit shaky, because this g behaves really, really strangely. Like, we don't really know it very precisely, as you can see. Only three digits are known. The fourth digit is already under heavy suspicion, let's say, because these are the various measurements, and you can see that they don't really agree between each other. Okay, so maybe the equivalence principle is something worth investigating, let's put it this way, okay? But yeah. And so, what about my own definition? Well, it actually stems from the inertial property of mass. So, as Eugene the philosopher, I would define mass as memory about the state of motion. That's it. So, you have a lot of mass. It's really hard to change your motion. Your memory is really good in this respect. Some sort of, like a hysteresis effect, when you can magnetize a piece of iron, so it has a certain memory about the magnetic field. Well, in this case, it's the memory about the motion. It's like the remnant magnetism of previous motion, so to speak. And I'm saying the word magnetism metaphorically, obviously. Something like that.